What is up, everyone? Welcome to Lecture 5 of Contemporary Math. Today we're going to be talking about Chapter 3, Section 1 and Section 2, covering logic. To begin with, let's talk about this definition of statements. A statement really is just exactly what the definition states. It's a true or false sentence, but it can't be both simultaneously. It has to either be true or it has to be false. As an example, Nixon once said, "When the president does it, that means it's not illegal." Well, that statement was decidedly false historically. Another example is the statement that Lake Street is a street in Minneapolis, Minnesota. Or that there is a Lake Street in Minneapolis, Minnesota. So having said that, we've got this idea of what these statements might be, right? Like they're simple yes, no, true, false type of a sentence. We can represent those in symbolic logic using all sorts of symbols that we want to represent. Traditionally, we use P, Q, R, or S to represent a statement. Having said that, this is a math class, so we're going to get into how we might manipulate these statements and get something out of them, right? To begin with, let's talk about the negation of a statement. The negation of a statement is its opposite in a general sense of what that word opposite means, right? Having said that, we use either the tilde or this funky looking kind of sideways L to represent the negation of a statement. So, in this example, we've got P represents the statement, Clifford is red. So the Clifford, the big red dog, it's red. True. Cool. P is true. The negation of P is false. The negation of P would also be the statement, Clifford is not red. Okay. Next example, we've got Q being the statement, the White House is in Seattle. Definitely not true. If we were to negate that, we would say that the White House is not in Seattle, which is true. So this is where this idea of opposite is coming from. It is quite literally the opposite in its truth value. Having said that, there is another type of statement that I want to talk about today called quantified statements. Quantified statements are just simply statements that include the words all, some, or none. And these words all, some, and none are called quantifiers. Go figure. They give us a sense of quantity, hence the naming of all of this, right? Philosophers and logicians and mathematicians were not very clever when it comes to language. We try to keep things simple when we can. Having said that, let's look at a couple examples. So, for a couple examples here, I've got 3 generic examples of quantified statements and then 3 more specific examples. In these first 3, we've got all A are B, okay, some A are B, all right, no A are B. So what we're really saying here is, because these are general examples, we can make A be whatever we want. And we can rewrite these statements to say all, let's say A is cars and B is blue. All cars are blue. We could generally rewrite these statements and things like that and in forms like this, right? This is like the most distilled form of a quantified statement, is what I'm trying to say. So, having said that, we've got these 3 more specific examples. There are no cats that are not mean. But we can rewrite this to say all cats are mean. Okay, that's one thing we could do here, right? This is in fact congruent with this particular a general example. Then we've got the example, some people are bigots. All right, well, fits exactly with what that second general example was. And then all dogs are not mean. We can rewrite this to say no dogs are mean. And it would have the same exact meaning. It would be congruent with this. So, the point really here is, in general, when talking about quantified statements are going to be of one of these three forms, or something that can be rewritten in one of these three forms. Having said that, let's talk about the negation of quantified statements. If we're going to negate the statement that all A are B, well, that would be equal to some A are not B. And if we were going to negate the statement some A are B, well, that would be equal to no A are B. We might be asking yourself now, well, hey, you left off the negation of no A are B. You're absolutely right, and I'm glad you asked. So, to answer why I left this off, I want to first talk about this idea of the double negation. If I have a statement, P, and I negate it, and then I negate it again, this is going to be equal to P. Double negations are equal to whatever the original statement was. So notice, if we negate no A or B, that's really the double negation of some A or B. So that would be equal to some A or B. So what I'm saying is the statement P is just some A or B. Negate it once, and we end up at no A or B. Negate it again, we end up back at our original statement. So this is the general gist of negating quantifiers. Okay, so what about compound statements now? What is a compound statement? Well, a compound statement is exactly what it sounds like. It's a statement made up of two simple statements, two or more simple statements. And we make these connections using connective terms. A couple common ones that we might use would be and, or, the inclusive or, I should say, or, if, then, slash implies. So what I mean here is there are two types of ors. There's the inclusive and exclusive or. And I'll talk a little bit more about that in a little bit here. But also, if, then, and implies, they're the same term in the sense of logic. If, then statements are implications. So when I say A implies B, it's equivalent to saying if A, then B. And that's all I was trying to say here, or all I am trying to say here. Having said that, let's dig into these compound statements some more. To begin talking about compound statements, let's start with and statements. So and statements are written using the kind of upside down V looking symbol. I like to think of it as an A with no bar through it. It just helps me remember that it's and. And the way this works is, let's consider we've got these two statements. P represents the statement dogs are great, and Q represents the statement cats are eh. Then to combine the two using and, we would have P and Q representing the statement dogs are great and cats are eh. In the case of the statement P and not Q, we would have dogs are great and cats are not eh. So this is kind of the idea that we're going to be seeing all the way through this, right? Like it's really not overly difficult. We're just going to be saying, we've got statement 1, statement 2, this thing in the middle that connects the two. Excuse me. So having said that, let's look at now the inclusive OR. I'll get into, towards the end of talking about OR, I'll get into the difference between inclusive and exclusive. So give me a second on that. Having said that, OR is written with a V, a giant looking V. And we can think of it by looking at this example I've got here. P represents the statement, Star Wars is great. Q represents the statement, Star Trek is great. P or Q represents the statement, Star Wars is great, or Star Trek is great. Which at first, it kind of sounds like I'm saying one or the other, right? Except for the fact that this is the inclusive OR. So what I'm really saying is either Star Wars is great, Star Trek is great, or they're both great. It can include both of them. This is what the inclusive OR means. The exclusive OR called XOR, what it is just one or the other. You can't have both. It's either this is true, that's true, or they're not true at all. That's the idea of OR. Moving on then to if-then statements. They're written using an arrow pointing to the right. Okay. And as an example, we can look at the statement, Anakin Skywalker is good. Or, my mistake, we can look at P representing the statement, Anakin Skywalker is good. Q representing the statement, Darth Vader is good. And this statement, P implies Q, it would represent the statement, if Anakin Skywalker is good, then Darth Vader is good. And down here at the bottom, not P implies not Q. It represents the statement, if Anakin Skywalker is not good, then Darth Vader is not good. And this is really the idea of what we're going to be talking about for the next couple of days. In our next lecture, we're going to talk about truth tables and how we can use truth tables to discern the truth values of these types of statements. Having said that, if you have any questions, feel free to ask. Have a good one, guys.